In this video, I'll be describing the bias conditions of a MOSFET: accumulation, depletion, inversion, as well as the flatband condition. So I've introduced 3 bias regions and 1 bias point. Just to summarize, the 3 bias regions are accumulation, depletion, and inversion. And the 1 bias point is flatband. Flatband is in the depletion region. The inversion is also included inside the depletion region. It's a special case of depletion that we're going to talk about this time. Let's start with a little bit about each of them. Accumulation first. Here's the MOS structure. So we have a degenerately p-doped gate and an N body. And you're in accumulation if you have a bunch of charge carriers from the N body, electrons in this case, N body, bunch of charge carriers accumulated at the interface. That's why it's called accumulation. Now, what makes that happen? If you put a bias voltage on the gate that pushes the conduction and valence band of the gate down, then you will bend the bands in the body downward as well. They're somewhat influenced by that because it's also the same thing as putting a negative voltage on the body, which pulls these bands up. You have an area just near the interface where the conduction band edge is closer to the Fermi energy than it is in the bulk. And so that's why you get an accumulation of excess charge carriers here. Now, why does that happen? It's this barrier potential that has to be maintained, the 3.1 electron volt barrier potential between the conduction band edge of silicon, whether it's degenerately doped p-type or n-type. It has to be 3.1 eV between the conduction band of that and the conduction band of the silicon dioxide. So in order to preserve that 3.1 eV, this bending happens to issue forth a little bit of correction to the pulling up of the band edges that happened in the bulk. That's a qualitative explanation for why it happens. What happens is the important thing, that you have bending of bands downward and it accumulates. I find it easier just to think about how you put a positive voltage on the gate, the bands in the gate material, which is made out of silicon, move downward because the positive voltage got put on them. The bands in the body, the N-type body, can sense that a little bit, and at least near the interface they want to go with it. I think of it that way. It's just a nice qualitative reminder. We can define a few potentials here. We have then the oxide voltage is the voltage drop across the silicon dioxide, so V sub OX. And then there's phi sub S, which is the surface potential. It's the potential that's created by the band bending. It's the amount of band bending that happens. Q times phi sub S is the amount of band bending. And if you add those two together, that's the added voltage beyond flat band. Because at flat band, there's no slant inside the oxide, and there's no bending of the bands in the N body. At flat band, everybody's flat. These two quantities, V oxide and phi surface, are 0 at flat band. The sum of them, showed here, fix that. The sum of those two voltages is the added voltage beyond flat band. So it's the value of the gate voltage minus whatever the gate voltage needed to be at flat band. Just to keep in mind that N and P body give opposite situations. For an N body, the gate voltage is positive. The flat band voltage for an N body is positive. You might want to jot this down. The typical value is around plus 1 volt for the flat band voltage with an N body. And for P body, it might typically be minus 1 volt. So the gate voltage is very positive in order to go into accumulation with an N body. So decrease that voltage from very large down, down, down. Finally, we get to flat band. And so what happens as the voltage is being decreased is these bands in the gate are going up because the voltage on the gate is being reduced. So they move upward. You just keep moving them up. Think of it as an animation. I keep moving the bands up by decreasing the gate voltage until finally they're at the same level on both sides. Now, when that's the case, the oxide voltage is now 0. There's no voltage drop across the oxide. That means everything has to be flat. And the reason why is because you have to maintain the electron affinity. For the oxide, the electron affinity is 0.9 eV, electron volts for silicon dioxide. So everywhere along the oxide, the vacuum level is 0.95 eV higher. For silicon, it's 4.05 eV. So everywhere along the silicon, the vacuum level has to be 4.05 eV higher. But if you take away the slant, you flatten out the vacuum level. And so you flatten out the conduction band edges so that they can maintain their 4.05. They maintain their electron affinity difference, which I have not illustrated here. When you make the oxide voltage flat, everything's flat. And again, the difference between N-body and P-body, for P-body will be typically negative. Now we continue to decrease that gate voltage. Lower it, make it lower than the flat band. So for an N-body, it might be about +1 volt. We just go to something slightly lower, like half a volt, 0.2 volts, 0 volts, still okay. -2 volts, still okay. We're in depletion. So as long as we're less than flat band, whether the gate voltage is positive or negative, as long as it's less than the flat band level, which for an N-body is positive, it's okay. So any negative gate voltage will have us in depletion, and any positive gate voltage that's less than the flat band voltage will have us in depletion. Why is it called depletion? As you continue to decrease the gate voltage, these gate bands keep moving up. Now they go up higher and higher, so now they start to drag the N-body band edges upward. The N-body band edges near the interface are going to want to follow as much as they can, follow what the gate is doing. And so they will move up. Now, when they move up, the difference between the conduction band edge and the Fermi level gets larger, meaning that in this region there are no carriers, no thermally activated electron carriers. All of the electrons in this region have left the region. You're stuck only with those positive donor ions. That is a depletion region. So that's why it's called depletion, because the phenomenon that occurs right here is identical to depletion. It is depletion. I will continue to call out the oxide voltage and the surface potential. They still have the same meanings as before. You'll spend almost all of your time thinking about depletion, which is a big region. Flat band is where it begins. As long as you're less than the flat band voltage, you're in depletion. There is a certain case which is worth noticing. Is notice how the Fermi energy in the bulk is close to the conduction band edge. But when you get over here to the interface, the difference between the Fermi energy and the conduction band edge grows. That happens because the gate voltage was reduced. So what if you keep reducing the gate voltage? What happens? The bands keep bending. This is the valence band. It keeps bending upward too. You know what's eventually going to happen? It's going to just keep going up until it might run right into the Fermi level, the quasi-Fermi level, which is supposed to give you electron carrier concentration. That's inversion. We'll have a voltage called the threshold voltage that as long as the gate voltage has been driven below that, you're in inversion. For an N-body, it'll be a negative number. I should have included that there. You'll be in a negative voltage. You'll be down low. You have to pull these gate energy levels way up to make this happen. Let's talk first of all about what happens with charges, and then we'll talk about the voltages. Again, you're still in depletion. Inversion is a bias region, but it's a bias region that is contained within the depletion region. Top of the inversion region is where you're at the threshold voltage, V sub T. So you still have these depleted dopant ions, this depleted region, these dopant ions with no electrons around to cancel out the charge. But something else happens too. Besides a bunch of positive dopant ions, that's what they are, they're positive. And we go way back to an earlier chapter to calculate how much charge is in that region, or you just use some common sense. You take N sub A, the number of dopants per cubic centimeter, multiplied by the width, W sub DEP is the width of this region, and then multiplied by Q, and you have the charge. And of course, it's not really that simple because it's not a brick wall, but you know what? The step function actually gets us everywhere because the little error involved is always housed within logarithms and really doesn't matter. So that's what we use for the depletion charge. But down here, it's not depletion charge, it's something else. These are holes. Because the valence band edge has gotten so close to the Fermi energy, instead of thermally activating electron carriers, you activate holes. So this whole region here, right of this red dashed line, is hole carriers. It has turned from an N-type semiconductor into a P-type semiconductor. That's why it's called inversion, because that change has happened. The bulk is N-type, but you get this thin little channel near the interface. That's P-type. And it's P-type because the valence band got bent up close to the Fermi energy. And so now if I ask myself, how much charge is there in this area? There are two sources, and by the way, they're not the same size either. The size of the depletion charge is the depletion width, and the size of the inversion charge is the inversion width, which is not going to be the same. If I figure out that inversion charge, and we're going to go over ways to do that, and I add it to the depletion charge, which is that, I will have the total charge in the substrate that is in the N body. The N body is a substrate, so that gives the total charge there. If I don't put any voltage on the gate, then I'm in thermal equilibrium. The Fermi energy needs to be a horizontal line all the way across. So if I take away all gate voltage, just set that to 0, this Fermi energy on the N body has to be at the same level as the Fermi energy in the gate. Any difference between those Fermi energies is because of the gate voltage that was applied. So Q times the gate voltage is the difference in those Fermi energies. I'm writing it this way. Just look at the top line because we're talking about N body in the illustration. The gate voltage times Q is the Fermi energy in the N body minus the Fermi energy in the gate, the P gate. Now I write it that way instead of the other way. You might say, why don't you say E Fermi in the gate minus E Fermi in the body? Because I need this to be able to become a negative number. The gate voltage in inversion is inevitably going to be a negative number. The gate voltage for depletion could be negative or positive. I need it to be negative, E Fermi in the N-type, minus E Fermi in the gate. That's certainly a negative number because that E Fermi in the N-type body is lower. That'll be a negative number, and it indeed takes a negative voltage to drive you to that point. Now if I go back and look at just the plane of depletion, where I show the Fermi energy in the body higher than the Fermi energy in the gate, again, E Fermi in the body minus E Fermi in the gate then will be positive until I get to the point where the Fermi levels are at the same place. So at 0 bias, when the gate voltage equals 0, this Fermi level is at the same level as this Fermi level. And then a negative gate voltage brings it lower. I can relate that to the voltages in the oxide because at flat band, these voltages are 0. At flat band, V oxide is 0 and the surface potential is 0 at flat band. So at flat band, whatever the gate voltage is, it's the flat band voltage. As you bring the gate voltage even lower, these guys become non-zero. These guys are negative numbers. So the oxide voltage and the surface potential in inversion are negative numbers. This is really important. These two things that just appeared here will help us to define the condition that makes inversion happen. That is the condition where the surface becomes the other type of semiconductor. So let's look at these two differences here. Look at where the valence band arrives at the interface, and you look at the difference between that energy and the Fermi energy. And then you go deep in the bulk and you look at the difference between the conduction energy and the Fermi energy. When these two are equal, which are kind of not quite depicted as at the moment, but when these two become equal, then you have as many electrons floating around in the conduction band deep in the bulk as you have holes at the surface. And when these two guys are equal, the surface is as p-type as the bulk is n-type. And that's the inversion condition. So when these two differences in energy are set equal to each other, then the semiconductor is just as much p-type at the surface as it is n-type in the bulk. There's this expression that's derived in Chapter 5. It's the second of these two that just appeared. It's an expression for the surface potential when you reach threshold, which could be a very useful thing to know. And it's actually not hard to figure out if you have this expression. 2 times 0.026 electron volts, that's kT over Q, times natural log of the doping level in the body, divided by n sub I, which for silicon is just 10 to the 10th. So it's actually a very straightforward thing to figure out. What's not so straightforward is the derivation of this expression presented in not just our textbook, in textbooks in plural. So I wanted to do a little aside here and talk about it. But first, it's a little different for NN body and for P body, but you use the doping level. That's the difference, doping level and the sign out front. Let me pause for a moment and talk about where this expression comes from. It's equation 5.4.2. Well, you need to read through that section 5.4 and work this out on your own. In fact, that's what I do. When I read a book like this, I have a pencil in my hand and I'm deriving those equations, because reading equations doesn't do much. And I hope that's what you're doing too as you read this book, that you are working out the derivations that are alluded to in the reading. And this is an important one. So I spent some time trying to derive equation 5.4.2 and I got stuck. I got stuck because it wasn't this. There was a factor of n sub c upstairs and a factor of n sub v downstairs, and I thought, well, that's a different expression. So do that yourself. Attempt to come up with this expression and find that you don't get this. And I said, well, but the difference is a ratio of n sub c over n sub v, which would have to be 1 in order for the equation in the book to be right. And then I scanned back up a little bit and realized the author actually says, let's make the assumption that n sub c equals n sub v, which if you take a look at table 1-4, you realize is not true. But is it a problem? They're different by 55% for silicon. They're different by a couple 100% for gallium arsenide, but let's just look at silicon. So in silicon, if you made this assumption, whatever's in this logarithm will be wrong by a factor of 1.55. But it's in a logarithm, so it really isn't going to be a big deal. N sub I is 10 to the 10th. The typical doping level is 10 to the 17th. Okay, so try them. Natural log of 10 to the 17th or 10 to the 10th is 16.1, but shifted up by a factor of 1.55 and you get 16.5. So using typical values, yeah, this assumption is off by 2.5%, which you may have figured out by now in this business. This is not a precision business here. So that's something you could probably live with. But I also, likewise, it's not that big of a problem to actually use the right expression. But go ahead, let's use this expression here for the threshold surface potential at threshold. Okay, that was my aside. Go through that on your own. Review example 1-5 for another justification for going ahead and saying this. So let's get back to the inversion condition. The gate voltage at the threshold to inversion is the flatband voltage plus the oxide voltage plus the surface potential at threshold to inversion. I'm going to do a little replacement here. I'm going to say, okay, at the threshold to inversion, all of the voltage drop across the oxide is due entirely to the depletion region. And so I'll go ahead and say it because you haven't actually started to gain any hole density in the valence band. Let's go back and look at that at conversion. So right at threshold, you're just at the voltage where you're able to excite holes. Right at threshold, so far the hole density there is 0. You have to go to even a more negative gate voltage to get any holes to actually show up. So right at threshold, we'll say that charge is 0, but not the potential. Phi sub s is non-zero. So that's what we use for the oxide voltage. It's a capacitor, right? Let's talk about that. We're bringing in capacitance here. So the voltage, V is Q over C, right? Q equals CV is the definition of capacitance. And the capacitance we're talking about is the capacitance of the oxide, because we're talking about the voltage of the oxide. So you can say the oxide is a parallel plate capacitor, and the charge on the two sides will be equal and opposite, and divided by the capacitance. Now, why the minus sign? Oxide voltage is supposed to be a negative number. There's no such thing as negative capacitance. Q and Q equals CV is intrinsically a positive number because it's plus and minus Q on either plate. So that's why there's a minus sign there. Let's put in what we have for the charge in the depletion region. We suggested that expression before, and so let's use that. And we have to deal with the width of the depletion region. Well, we have a way of doing that. We talked about this in a previous chapter, that the depletion region width is the square root of the potential, dielectric constant times the potential barrier over the charge contained. We use that equation. So go ahead and put that in there, but what do you use for the potential barrier? Well, we'll use the surface potential threshold because the surface potential is the voltage that we actually have. So I'm going to use that. And I realize I have something that's quadratic in surface potential threshold. Oh, okay. It's quadratic. You can solve that, right? And in fact, for problem 5.5b, you're going to have to in order to get the doping level, which actually wasn't given there. So use this when you get to problem 5.5, part B. We're going to come back actually to talk more about the setup for problem 5.5 in the next one.